Dear students, Assalamu alaikum wa rahmatullahi wa barakatuh. Today's topic is Fourier transform, properties of Fourier transform. Okay, so our first property is Fourier transform is linear. It is like Laplace transform, like as Laplace transform is linear. That is, Fourier transform is linear here. If we take a function, you see, function of Fourier transform f of a t plus or minus, it may be plus or minus b of gt. Now, this one will be a plus Fourier transform of ft plus or minus b Fourier transform of gt. B and a is constant, right? If Fourier transform of ft is fs, we can write a fs, and if Fourier transform of g of t is gs, then we can write plus or minus b gs. Right. So from the definition of Fourier transform, we know Fourier transform of f of t can be written as Fourier transform of f of t equals to, we can write 1 by root over of 2 pi. It is negative infinity to positive infinity. Then f of t e to the power I s t dt. So if it is ft, it will be ft. If it is zt, it will be zt. Now, our ft is here, you see, ft is a plus ft, a times ft plus b of gt. Right. So we can write 1 by root over of 2 pi by the definition of Fourier transform using this definition. Actually, you can write 1 by root over of 2 pi. Limit is negative infinite, positive infinite. This one is function of t, a f of t plus or minus it may be plus or minus. So plus or minus. So we can write 1 by root over of 2 pi, negative infinity, positive infinity. Then we can distribute the integral sign on both functions. Negative infinity, positive infinity, a f t e to the power ist dt. Similarly, plus, here plus or minus, you can write my negative infinity, positive infinity, b g of t e to the power ist dt. So we can take the constant in the left side of the integration. That is a 1 by root over 2 pi negative and positive infinity ft e to the power ist dt. That is like as if we want to integrate 3 x squared dx, we can write 3 times x squared dx. So similarly, this constant a can be taken in the left-hand side of the integration, like b of constant b can be taken in the left-hand side of the integration. So now you see in the second bracket, these are the Fourier transform of ft. If we see the definition of Fourier transform. So this one is the Fourier transform of f of t. If it is plus or minus, it is plus or minus, it is plus or minus, and b is constant, so we can write b here. Then this one is the Fourier transform of gt, so we can write Fourier transform of gt. Or if the Fourier transform of ft is fs, so we can write a fs plus or minus b gs for the Fourier transform of g of t. Do you understand? Do you have any question, please, about it? Please give your comments or give your feedback, please.
Yes, sir. Good, good.
Is it okay now?
Yes.
Okay, so now this one is the first property. Fourier transform is linear. Okay, so our next property will be shifting property. That is Fourier transform of f of t minus c can be written as e to the power I s c and times Fourier transform f of t. So by definition, again, if you write the definition of Fourier transform, already I have written in the last slide, that is Fourier transform of ft can be written as 1 by root over of 2 pi, then negative infinite to positive infinite, f of t e to the power I s t and dt. Sometimes we write here x. If it is x, this one will be x, f of x, e to the power I s x, and this t will be replaced by x. So variable does not factor here, but keep in mind that in Laplace transform, the limit, lower limit is zero. In Fourier transform, the lower limit is negative infinite. And the total, that is the function is defined in the whole real line from negative infinity to positive infinity, right? So there are three conditions. Function must be defined on the whole real line. That is, the function must be defined from negative and positive infinity. Then number two, function must be piecewise continuous. And third condition was f of t must be integrable. Must be integrable. The modulus value of f of t must be integrable. If a function satisfies these three conditions, then we can take the Fourier transform that I have said in the last class, which was conducted in the face-to-face mode. Now, the Fourier transform definition of the Fourier transform is such as, so if we want to take the Fourier transform f of t minus c, so function of t f of t minus c, right? So now we can take a new variable t minus c as u. If we take t minus c equals to u, so we can write t equal to u plus c. C is a constant term here. So now if we take differentiation with respect to u here, so we can write dt du will be 1 plus 0. That is dt du equal to dt du equals to 1. So we can write dt equals to du. du. Do you understand? So now, uh, here you see the limits will be same. We need not to change the limit, because if we take lower limit negative infinity for t, so it is negative infinity u plus c. So u will be negative infinity. When you take positive infinity for t, so we can write positive infinity equal to u plus c. So u will be positive infinity. That's why we need not to change the lower limit and upper limit. It will be same. So now 1 by root 2 pi we write here, and t minus c will be replaced by u that we consider here. T minus c equals to u. So here it will be ist, that is t will be u plus c. That's why you write u plus c, and it will be is times du, because dt equals to du. Now, in this in the right hand side, the variable is considered as u here. So we can write e to the power I, e to the power I s u times e to the power isc. If we expand this one, so e to the power isc is constant term, because in this expression u is variable, so we can take e to the power isc in the right hand side of the integration. So we can write here negative in positive infinity f of u, and it will be isu du. So you see, this one is the definition of the Fourier transform, including 1 by root 2 pi. So we can take it by ISC in the left hand side, and this one is the definition of Fourier transform. That's why we can write e to the power ISC times Fourier transform of f of u, or Fourier transform of f of t. That is e to the power isc multiple of f of s. As the Fourier transform of f of t is f of s, so we can write e to the power isc times f of s. This property is known as shifting property. Like in Laplace transform, we have seen in the there is another property, shifting property. So do you understand this property, please? Do you have any question? Please give feedback. Put your feedback, please. Have you listen me?
No, sir.
Okay.
No problem.
Yes.
Okay. So now it is a scaling property. It is also like a Fourier Laplace transform. You see the Fourier transform f of ct here, c of t. We can write c is a constant, so we can write 1 by f of 1 by c f of s by c. So you have to keep in mind that the Fourier transform of f of t can be written as 1 by root over of 2 pi negative infinite to positive infinite f of t e to the power ist dt, and we can write this value equal to function of s. Okay, so using the definition of Fourier transform, basic definition, f of ct can be written as 1 by root over 2 pi fct can be replaced by f of ct. Here it is f of t. Okay. So again, we can consider the variable ct equals to u. Here c is constant. Okay. So we can write t equal to 1 by c u. Now if we take differentiation with respect to u, dt du, we can write 1 by c 1. That is dt equal to 1 by c du. That's why we have to put the value of dt as du by c. Now, Fourier transform f of ct can be written as 1 by root 2 pi. Just put the value of ct here, ct is u, right? So t equal to, what is the value of t? From here, you see t equal to 1 by cu, that is u by c. We write here u by c. Okay. And du equals to, dt can be done du by c. That's why I write the value of dt equal to du by c. Now, this 1 by c is constant, so we can take in the left-hand side of the integration. That's why we write here 1 by c. And 1 by root over of 2 pi, negative infinity, positive infinity, fu, e to the power minus s by cu du. So if you are, you can read written here, you can write as root over of 2 pi, negative infinity to positive infinity, f of u d e to the power I s u du can be written as f of s. So if it is s, we can write f of s. But if it is s by c, we can write it is f of s by c. That's why you write here the value of this integral as f of s by c. Okay, so it is proved here. So if you have any question, then you can ask me. Do you understand? And put your feedback, please. Do you have any question, please, regarding this case?
No, sir.
Okay, so now differentiation property. It is very important one for you. differentiation property. We will use this property uh, in future for solving the differential equation. Actually, a Laplace transform is used for solving the ordinary differential equation. I repeat it. Laplace transform is used for solving the ordinary differential equation, which are initial value problem. But Fourier transform is used for solving the partial differential equation, which is boundary value problem. So what are the difference between initial value problem and boundary value problem? Initial value problem, it contains the initial condition. And boundary value problem, it contains initial conditions, including boundary conditions. That's why to solve the boundary value problem, we will use Fourier transform. Okay, so I will solve a problem in the next class, which is regarded as the partial differential equation and is known as heat conducting partial differential equation. I will solve it. Now, actually, to solve this problem, we need to know the properties of Fourier transform. How can we deal this property? In this problem, we will see if ft is piecewise continuous and negative infinity, positive infinity, it is already given. You know, without piecewise continuous, we cannot find the Fourier transform. So this one is the Fourier condition for finding the Fourier transform, and the function must be defined on negative infinity, positive infinite. Okay, so and ft tends to 0 when mod t tends to infinite. And ft and f prime t are absolutely integrable. Without absolutely integrable, we cannot find the Fourier transform. And then we have to show that Fourier transform, first difference of Fourier transform can be written as minus is times Fourier transform f of t. So if we want to use again the basic definition of Fourier transform that was already have said, Fourier transform of, again I am writing, Fourier transform f of t can be defined as 1 by root over of 2 pi negative infinite to positive infinite function of t e to the power ist dt, right? So now you can use here the Fourier transform ft. This ft can be replaced by f prime t. If we replace f prime t here, it will be f prime t also. That's why function of t is replaced by f prime t in the left hand side and in the right hand side also. Okay, and we have a formula which is known as integration by parts. You can remember integration of u dv can be written as uv minus integration of v du. If the limits are a to b, it will be a to b, and this limit will be a to b. In this case, it is negative and positive infinite. Now, which one we consider u here? We can consider let u equals to e to the power ist, right? E to the power ist as u. Then dv will be, as it is u, then dv will be this value, f prime t dt. So dv will be f prime t dt. Okay, so we can integrate on both sides. So integration of dv will be v, and integration of f prime t will be f of t. Okay. If we take integration on both sides, then left hand side will be v and right hand side will be f of t. So now put the value of u v here. The first term is u times v. So u is e to the power ist, this one is u, and v is f of t. So u v minus, you can write minus integration of v du. V is ft and du is, you can find the du from here as u is e to the power ist, e to the power ist. So we can write du will be is e to the power is t and dt. That's how you write is. It is is, not is in the English language. It is I and s, multiple. Is of ist dt. Okay, so now is is the constant term, so we can take in the left-hand side of the integration, and that's what we write here. So I is my, it is my, there is a negative sign, so you get minus I is, and 1 by root 2 pi, negative and positive infinity, ft is by ist dt. You see, this one is the definition of Fourier transform. So you have a question, how it will zero, right? So in this expression, you see, ft tends to 0. The value of ft will be 0 if t is positive infinite or t is negative infinite. So in this case, the upper limit is positive infinite. So in this case, ft is 0, and negative infinite, it is even minus st, it is also 0. So that's why this value will be 0 for upper limit and lower limit. And that's why we write here, this value is 0 here, you see. And we have minus is function of t ft. If the first derivative, f prime t will be minus is function of t. Now, what will be if we take the second order derivative, that is f double prime t? Can you say anyone, please? What will be f double prime t? Please, can you give a free feedback using the concept of Laplace transform? Like, do you understand this one, please? Would your feedback? From C, from this statement you see, f prime t can be written as in such way. That is, already we have shown that f prime t equal to minus is Fourier transform of ft, right? Now, if we put, suppose you can consider, sir, we can write g of t equal to f prime t, right? So now if we take in differentiation, you get g prime t equal to f double prime t, right? So if Fourier transform of f prime t is equal to minus is ft, so we can write Fourier transform of g prime t can be written as minus is Fourier transform of g of t. Okay. Similarly, so g of t is, sir, what is g of t? G of t can be written as from here f prime t. So Fourier transform of f prime t. Now f prime t can be written as from this expression, we can use again is minus is Fourier transform of f of t. That is minus is whole square Fourier transform of f of t, and g prime t can be written as f double prime t. So Fourier transform of g prime t can be written as f double prime t. So the second derivative of the function can be written as minus is square Fourier transform of f of t. Similarly, we can find third derivative, fourth derivative, or nth derivative. For nth derivative, we can write Fourier transform nth derivative minus is to the power n Fourier transform f of t, where n must be integer type as it is derivative, right? First order, second order, third order, or fourth order. So, do you understand? Do you have any question, please? If you have any question, then you can ask me. I will try to solve it.
No, sir.
Sir, can you give a brief discussion again, please, shortly?
Which one?
Sir,
Repeat.
the last part. I didn't quite understand.
Which one, please? Please repeat your question.
Sir, I didn't understand the last part. Like my net connection was unstable. Can you repeat that?
Can you repeat, please? So in the last class, we have solved this problem, Fourier sine and cosine transform for infinite series, infinite form. If we take Fourier sine transform, the first letter of sine is S, that's why we write Fourier sine transform, and it is Fs, and that's why we write 0 to infinite ft sine st dt. And for cosine transform, it will be C. That's why we write Fourier transform C, ft, fcs. And this term will be cos st dt. Now, if we want to solve a problem for Fourier sine transform, ft can be written as it is equal to minus at here. So just to put the value of ft here, ft is e to the power minus at, and sine st it comes from definition. So that sine st, the minus it is sine st. Now you can use the formula, use this formula, e to the power a star. Here star is considered as t. Star is considered as t here. Okay. So e to the power a t, a is negative a is negative a, and b is s. Right. So a is negative a and b is s in this problem. So now we can use e to the power a star, a star means t. So we can write e to the power a t. E to the power a is negative a. E to the power negative a t, we write here, divided by 1 by a square. A is minus a whole square, and b is s square. And that's why we write here a square, s square. Then a is negative a in this problem. That's why you write a negative a. And then b star, b is sine b, b is, what is b? B is s. So we write sine st minus b, b is s. That's why we write minus s, and cos b star, that is cos st. Now we put the value of infinite and 0. When it put infinite, e to the power negative infinite, e to the power negative infinite, this value is 0. So after multiplication, this result will be 0. 0 times n will be 0. Now if we put 0, then it will be e to the power 0 will be e to the power 0 will be 1. So 1 divided by a square plus s square and minus a sine 0 is 0. And we can write minus s cos as. I'm sorry, cos 0. Cos 0 is 1. Okay, so it is minus s, and we have a formula from upper limit. There is a negative sign, that's why it will be plus sign. So plus s by a square plus a square, s square. So in this way, you can find the sine transform. Similarly, we can find the cosine transform. F of t, it is by minus 8 in this case, and st is cos st. It comes from the definition. So you can use this formula again. And the previous one, it was sine, and in this problem, it is cos. So you will get the answer a by a square plus s square. Similar process when we put negative infinity here. So e to the power negative infinity will be e to the power negative infinity. This value is 0, right? So 0 times n value will be 0. Then minus, again, if we put the value of t equal to 0, so we can write minus a, and cos 0 will be 0, cos 0 will be 1, and sine 0 will be 0. So it will give plus a. So a by a square plus s square, it comes from this one. So a by a square plus s square, when we take cos transform, and when we take sine transform, it is s by a square plus a square. Okay. Now, if you take the Fourier transform, sine transform of this function of t equals to 1 or 0. So when 1, it is minus a to positive a. And when 0, when t tends to negative infinity to negative a, and a to positive infinity, right? So we have a definition for Fourier sine transform 0 to infinite is ft sine st dt. Okay, so 0 to infinite can be written as 0 to a first. Ft is 1 here. So 1 times sine st dt plus a to infinite. So when a to infinite, in that case, Fourier, the value of function is 0. So we get 0 times sine st dt. You see this value is 0, and that's why we write here 0 to a sine st dt. We write 0 to a sine st dt. Now integration of sine st will be minus cos st by s. Now put the value of t equal to 0 and t equal to a. If we take t equal to a, we can write 1 by s cos at. T is a. So cos as minus cos as by s. If we take 0, it will be cos 0 is 1, and minus minus will be plus 1. That's why we write here 1 minus cos as. So this one is the Fourier sine transform. Similarly, we can find the Fourier cosine transform. Similar case. It is just cos, and this one is sine, and 0 to a, and another term will be from a to infinite. 0 times 0 times cos st dt. So this one will be 0. That's why we have to integrate only cos st. Cos st integration of cos st will be sin st by s, and put the limit here, you will get this answer. So do you understand, dear students? I have solved this problem at your class also on face-to-face mode. If you have any question, then I can again repeat it. Do you understand, dear students? Please put your feedback.
Yes, sir, understand.
Hello.
Sir, understand.
So now Fourier transform, finite Fourier sine transform, or finite Fourier cosine transform. For finite, we write here Fs here, S for sine. So finite Fourier sine transform can be written as 0 to L Fx sine n pi x by L dx. Already I have said that it can be t, so x will be t ft sine n pi t by L dt. No problem. So in this case, finite, okay. So the function will be defined from 0 to L. So in this problem, the function is defined from 0 to 4. So L is defined as 4 in this case. So Fourier transform, sine or cosine transform can be occur for two cases. One is infinite and the other one is finite. So in this case, it is finite, 0 to 4. So now, Fourier, if we take Fourier sine transform, we can add 0 to, keep in mind that in the previous it was infinite. But as the function is defined here, 4, 0 to 4, and it is also given here finite Fourier sine transform, finite, right? So if you will give in Fourier sine cosine transform or finite Fourier cosine transform. If it is Fourier cosine transform, it will be infinite. If it is finite, it will be given here, finite Fourier cosine transform. So now, if we want to find Fourier sine transform or cosine transform, in this case, we first find the Fourier, first case, that is find Fourier sine transform. That's why we write here 0 to L. 0 to L is 4 here. That's why we write 0 to 4, and f of x is 2x, right? So as 2 is a constant, so we can take in the left-hand side of the integration, we write x sine n pi x by 4. If this L is 4, we write n pi x by 4 dx. So you can integrate this one using integration by parts that I have shown in the last slide, or you can use the tabular method also. That is x, difference of x is 1, and difference of 1 is 0. Integration of sine n pi x by 4. Integration of this one will be minus 4 by n pi cos n pi x by 4. And integration of this one will be minus 4 times 4 will be 16 n square pi square sine n pi x by 4. So now you can write here, the first term is minus 4x by n pi cos n pi x, minus 4x by n pi cos n pi x by 4. And the second term will be minus, and minus will be plus 16 by n square pi square sine n pi x by 4. Now we put the value of x equal to 4 and x equal to 0. So if we put x equal to 4, it will be 4 times 4 will be 4 here. And cos, if we take here x equal to 4, 4 and 4 will be cancelled out. That's why we write here cos n pi. And if we put here sine, this one is 4, so it will be sine n pi, 4 and 4 will be cancelled out. That's why we write here sine n pi. If we put 0, so this value is 0. So 0 times 0 will be, any value will be 0. And if we put 0 here, sine 0 is 0, sine 0 is 0. That's why for lower case, the lower limit, this value is 0. So now we can write here 2 times 4 times 4 will be 16, and times 2 will be minus 32 by n pi. This one is cos n pi, and sine n pi is no 0. N is positive integer type actually. That's why this value is sine n pi is 0. we write here minus 32 by n pi cos n pi. Cos n pi is negative 1 to the power minus 1, or we can write minus 1 to the power n plus 1, 32 by n pi. So this one is our answer. This one for Fourier sine transform. Of course, it is finite, right? Similarly, we can find the Fourier finite Fourier cosine transform. Similarly, we can find the finite Fourier cosine transform. This cosine, C-O-S-I, cosine transform, using this one, the definition 0 to L, where L is 4 here, f of x is 2x, so we write 2x, and cos n pi x by 4, L is 4, and use the tabular method and put the value of x equal to 4 and x equal to 0. Your calculation will be this one. You can write also cos n pi equal to negative 1 to the power minus 1. No, there is no problem. So 32 by n square pi square cos n pi minus 1. Please keep in mind that I need these two integral value because this value will be used for the solution of partial differential equation. That's why I will not calculate this integral again. So I just use this result directly. Okay. So do you understand? Please put your feedback. Dear students, have you listened me, please?
Yes, sir. Yes, sir. Good.
Do you understand? Hello?
Yes. Yes, sir.
I cannot hear you, please.
Mm. We understand.
Okay, find the Fourier sine and cosine transform of the function del u del x first, and here it is find the finite Fourier sine transform and find the finite Fourier cosine transform of the function del u del x. Okay. Here you see Fourier sine transform can be written as function of xt 0 to L finite as it is finite. So f of xt sine n pi x by L. Okay. So in this case, L is L dx. Now, if it is xt, we can write f of xt. If it is del u del x, we just replace this one del u del x and here also del u del x. That's why you write here del u del x. In the left hand side, Fourier sine of del u del x and 0 to L. This one will be del u del x and sine n pi x by L dx. Now, using the integration by parts rule, that is from A to B, u db equal to ub from A to B minus integration of A to B v du. Use this identity actually. So we can consider u is as we can consider u is a sine of n pi x by L. So what will be du in this case? Du dx. Can you say anyone? What will be du dx? From here we can write sine. It will be my L by n pi cos n pi x by L u. And what will be dv in this case? dv is del u del x. So integration of dv, okay. Del u del x is u is a constant, so we can u prime. So u prime of dx, it will be v u. That's why you write here u. Okay. So u is this value u, and this one is v. V is u, capital U here. Minus it is 0 to L, and minus d minus v du. V is sine v is u x t, and du, the value of du is L by n pi cos n pi x, and dx will come here. So du will be my L by n pi. We write here L by n pi, L by n pi, L by n pi. There was a mistake, maybe. Oh, sorry, it is it is differentiation. So it will be n pi by L. I'm sorry. It is differentiation. So it is n pi by L. That's why you write here n pi by L, and and du n pi by L cos n pi x by L and dx. Just now put the value of L in the place of x. So L and L will be cancelled out. If we write L here, L and L will be cancelled out. So it is sine n pi. Sine n pi is 0. So this value will be 0. If we put 0, sine 0 is 0, this value will be 0 again. So we'll get here the first term will be 0. Okay. So minus n pi by L, 0 to L cos n pi x by L, u of xt dx. So you see this one is the definition of Fourier cosine transform. Which one? For u of xt. That's why we write here minus n pi by L, Fourier cosine transform of u of xt. Okay. Do you understand, please? Do you have any question? Do you have any question, please?
No.
Do you understand? Please do not write here the ID number. I will give a Google link. In that case, you can put your attendance there. You can just give a full feedback. Do you understand this one? Please say, give your feedback by sound. So we have
Good, sir.
find the Fourier sine transform. So this one is minus n pi by L FCN or Fourier cosine transform u of xt. Similarly, we can find the Fourier cosine transform. In the similar transformation is given here. In the previous it was sine, and in this case it is cosine transform. So FC is cosine del u del x, 0 to L del u del x cos n pi x by L dx. Now in the similarly, we use here and consider the formula here u is cos n pi x by L, and you can write dv equals to del u del x. So a d will be u in this case integration, and d du dx will be n pi by L sine n pi x by L, and there's a negative sign. Okay. So from formula, it will be negative plus negative will be positive sign. That's why we write a positive sign. And u is this value, and v is this one. This one is v, this one is u. And there is a negative sign. And this negative sign will multiple of negative and negative will be positive sign. That's why we write a positive sign. And n pi by L is here, 0 to L. And this value du sine n pi x by L, and v is u here. So now put the value of upper limit L and X. So keep in mind that L will be replaced by X and 0 will be replaced by X also. So if we put the upper limit L equal to X, so if we put here X equal to L, so L and L will be cancelled out, so it will be cos n pi and u of xt. So cos n pi u of x lt, sorry, x will be lt minus when 0, you can write cos 0 is 1. So that's why we write here minus u 0t, x will be replaced with 0. So u 0t and u lt. These are the boundary condition, u lt and u 0t. So cos n pi u lt minus u 0t, it comes from here. And in the Fourier sine transform, the previous slide you see, it was 0 because sine, multiple of sine n pi is 0 and sine 0 is 0. That's why this time was 0. And in this case, it is this value, so cos n pi u of lt minus u of 0 t. Now, for this case, you see u of xt sine n pi x by L. So sine n pi x by L, u of xt dx. Now we can write here cos n pi, you can write cos n pi minus 1 to the power n, you can also write here u of lt minus u 0t n pi by L, and this one is the definition of Fourier sine transform. So this one is the second proof. There is Fourier transform of del u del x. Fourier transform of del u del x can be written as this value. And I will use this identity in the next class, inshallah, the next Friday after your quiz. So finally, I would like to find the finite Fourier sine and cosine transform of del square u del x square. In the previous, it was del u del x, and in this slide, we will find the Fourier sine and cosine transform of del square u del x square. So already you have known that Fourier sine transform of del u del x is this one. In the problem 8, part 1, A maybe. So if we take, if we replace u by del u del x, okay, this u, if we replace u by del u del x, it will be, okay, please see here, del x of u. If we place u is del u del x, it will be del x del u del x. So it will be del x square u del x square. That's why in the left hand side, you can write Fourier sine transform of del x square del x square. And in the right hand side, minus n pi by L fc del u del x. So fc del u del x, the value of fc del u del x is this one, fc del u del x. This value, right? This value. That's why you write here fc del u del x is minus n pi by L minus n pi by L cos n pi u L t minus u 0t, this value. Okay. So the Fourier transform del square del x square will be this value. Right, sir? Now, just multiple n pi by L. Here, and here. So it will be n square pi square by L square. That's right, n square pi square by L square. And each term it is negative sign, so cos n pi minus, and it will be plus sign, plus n pi by 0 to, and this one. So similarly, we can find the Fourier cosine transform. Okay. So del square del square. That is, in this case, already we have known this formula in the previous slide I have shown. So u can be replaced by del u del x. That's why fc del square del x square can be written as cos n pi. U is replaced by del u del x. U is replaced by del u del x, and this is del u del x. Now put the value of this one, cos this one will be same. Only we have to find the value. Just put the value of del u del x. Fourier sine transform del u del x is minus n pi by L fc u of x. Okay. Already we have shown it in the previous identity. So Fourier transform of cosine transform of del square will be this identity. Thank you for today. I will apply, will solve a partial differential equation in the next class after your quiz. So do you have any question, please? If no, I will close the class.